Hello. So this is Ethic, and I'll be presenting our paper, ActiveNet, which is basically a computer vision based approach to determine lethargy. So a little bit about us. Me and Aditya Kawal are undergraduates at IIIT Gwalior. And during this lockdown, we were actually studying the impact of COVID-19. And we were quite interested to find out that the mean of the metabolic equivalent of task, which is basically activity, has dropped down significantly during COVID-19. So you can see in all these sections, the activity has dropped down significantly. Now there are quite reasons for this. So we everybody is forced to stay indoors because of lockdown, and there is a outdoor activity decline, and the low output with declined standards of physical activity has also played a role in a drop in physical activeness in total. So to actually tackle this, we thought of the objectives, what our objectives should be. So our objective was to build a system to detect activeness, which is abstract, and we should exploit a single monocular image of a targeted human, and we should do it in such a way that it is robust to different backgrounds, different postures, and it should run real time. Keeping in mind all this, we decided to keep it in an application setting so that users of our Slack workspace receive alerts when diminished levels of activeness are detected. So basically, our motive is to create this ActiveNet box. So we have a target human image. We pass it to the ActiveNet module. We get different activeness levels, which we'll talk about in just a bit. And if we find out that a person has low activeness, we'll trigger the alerts in a Slack workspace. So how do we go about achieving that? We achieve that using a multi-stage approach where our first module is human pose estimation. So what human pose estimation would do is in an image, it will give us exact localization of key points such as nose and shoulders and arms and wrists, etc. So it will give us the exact locations in the coordinate space. So we use the lightweight open pose estimate implementation, which is a heavily optimized version of the original open source implementation, which runs real time on CPU. So that takes off. So it was originally trained on MS Coco dataset, which has 17 ground truth points and plus two interpolated estimations. So the neck joint and the core joint could be basically taken as the 2D Cartesian plane of left and right key subjoints, like left hip and right hip, and left shoulder and right shoulder. So human pose estimation module, but what would it give us? It would give us the exact key points of the target in the coordinate space. And after that, we needed to convert it into an encoding. How do we do that? We convert it with a pose encoding module. So there was a problem in using the key points directly. So you see that there are two images, and these are essentially the mirror images of themselves. So if you take a look at overall in a context, the activity, the activeness, the person is it should be the same, right? But the exact key points that we get are in coordinate space, which will have which change quite a lot if we just mirror the image. So we need to remove any spatial context from these images. For that, we used angular representation instead of the exact coordinate spaces. We used angles such as you see that this person is sitting upright, so he has a high activeness, right? So take a look at the angles between nose, neck, and the right shoulder, and take a look at here: nose, neck, and right shoulder. Look at how these values change. So we use these as the features basically in the next module, which we'll talk about in just a bit. So our goal in this module is to encode the key points using a noble angular representation, which will basically give us a array of fixed length, which will have left shoulder, left elbow, left wrist, basically the angle between them, and the angle between these, and angle between these, like subsequently all the subset of joints that we chose the subset of joints in such a way that it captures the range of motions in most subsections of the body, in upper and lower body. So those encodings are basically classified into four levels using a traditional tree-based machine learning algorithm. What are those four levels? We define those four levels actually with a self-scrape dataset. We scrape dataset of internet. Let me just quickly tell you the levels of activeness which we have. So we use four-class division adapted for determining levels activeness of human. So this is level 1, this is level 2, this is level 3, and this is level 4. So you can see that it's the we can see that the activeness of the person is gradually increasing, which is abstract, right? You see the labels here, those labels are not the exact percentages but the labels that we give to the class, right? So between 50 to 75, above 75, between 25 to 50, or below 25, right? So how do we gain them? So we used keywords in normal Google search keywords such as army soldiers. Army soldiers are always in attentive position, so we scraped out 40 images of that class, and like sleeping while standing will give us level 1 activeness, which is basically the lowest level of activeness zones that we get. So we basically define those 4 levels, and let's suppose those encodings are basically classified into four zones. So let's say that the it's one of the encodings is classified, one of the frames, one of the humans is classified into low activeness zones, below 25 percentage to be more precise. So if it's classified into below 25 percentage, we raise an alarm system. We trigger an alarm system basically. So low activeness alerts run out to users of a Slack workspace. And how is that? Whenever an alarm system is triggered, we send an HTTP request to Slack workspace with a custom message, which could include the timestamp, which we see right here. So this is a Slack notification alert sample. So this is the notification alert bot. It'll tell us the attentiveness is below 25 percentage, and it'll tell us a timestamp when it was, and it could also contain the place where it was, and place as well as the person ID, right? So this is basically the overall view. Let us take a look at the overall system architecture. So we take a camera input. We If the frame is red, we extract the key points using a key human pose estimation algorithm. We extract the angles, angular representation, basically using the posing coding module, and then we pre-process the input using scalars and imputers, which we get from self-scraped dataset. We train the classifier, and we predict the activeness levels, so with the input, and we basically find out which of the 4 levels does that frame belong to. So if it belongs to high activeness, which is basically level 234, we'll just pass it. And if it's not, if we find out that the person activeness of person is level 1 for a contiguous k amount of frames, then we trigger the alarm system. So I'll just quickly give you a demo. Yeah. So you can see that we receive these Slack workspace alerts. Yeah. Uh, Let me talk about the actual implementations where it could be used. So we could use them in interviews, we could use them in online classes, in security surveillances, in video conferencing, in company meetings. We could use it in most of the scenarios. So we could use our solution that we built to in all these kind of implementations. So that brings to the end of our presentation. Thank you so much.